Hello and welcome to Diplomatic Derivatives. In today's video, we're going to talk about quotient groups. In our previous video, we explained normal subgroups and some theorems related to normal subgroups. So those are going to come handy when we discuss quotient groups because those concepts are part of this concept. All right. So make sure you check that video out first and become aware of all the concepts in normal subgroups and theorems as well, because the last theorem that we did is in relation to quotient group definition. All right, so let's see what is a quotient group. All right, so let G be a group and H a normal subgroup of G. Now what we are assuming, that we are saying that we have one group and one subgroup. All right, and this subgroup is specifically a normal subgroup. Now in the previous video we explained what is a normal subgroup. For a group subgroup to be a normal subgroup, it should satisfy the condition x h x inverse. That has to be the element of the subgroup. Okay, if this condition is true, it means that that subgroup is the normal subgroup of G, where x is element of G and small h is element of capital H, which is the subgroup, and this x inverse obviously is the inverse of this element x, right? And this element that is formed when we do x h x inverse belongs to H. Then we can say that H is a normal subgroup of G. So the condition, so how do we get the quotient group? We have to have a group G, and then H has to be the normal subgroup of G. Then the set G over H of all the cosets of H in G together with the boundary operation defined by HA HB is equal to HAB. What do we mean by this entire statement? Basically, in simple words, the set G by H is called a quotient group when it has cosets. So any group having all the cosets of H in G. So we have a particular subgroup which is a normal subgroup of G, and all the cosets formed of H in G. A set having all those cosets is known as the quotient group. Okay, so G by H is a quotient group here when H is a normal subgroup of G and all the cosets of H in G belong to G by H. Okay, now this is a theorem that we did in the previous video, that is HA/HB is equal to HAB, where HA is one right coset, HB is another right coset, and the product of two right coset is again another right coset, which is HAB. Okay, so this is the product of HA HB. Now where HA is element of G by H, HB is element of G by H, HAB is also element of G by H. Okay, now we know that when we talk about a group, okay, it has four group axioms. The first one, what is the first group axiom? It is closure, right? Now if you look here, we are saying that G by H is a group having cosets, right? So therefore each element is a coset. Inside G by H, each element of the group is a coset. Now when we talk about it being a group, it means it has to satisfy the group axioms, right? The first one is closure, and this particular theorem talks about that property, that is HA, that is first element, HB another element. The operation, that's multiplication, let's suppose, so HA HB gives another right coset, which is HAB, has to be inside G over H for G over H to be a quotient group. So that means that the group axiom is satisfied. So this theorem basically is a group axiom for quotient group. Okay, so this is the basic understanding of a quotient group. Now in case the operation is addition, so it will be H plus A, which is one of the right coset, adding with H plus B, which is another right coset, will give you H plus A plus B. So it's just the same thing, only here the operation is multiplication, here the operation is addition. For existence of quotient group, okay, for the existence of quotient group G by H, it is necessary that H is a normal subgroup of G. So this condition is very important. If G by H exists, it means that H has to be a normal subgroup, not just any subgroup. It has to be a normal subgroup. It means this condition has to be satisfied. Okay, that's what is a quotient group. Now we'll take an example and we'll try to understand with the help of an example. Find the quotient group G over H and also prepare its composition table when G is, this is the main group, that is 1, minus 1, iota, minus iota, and the operation is multiplication. Subgroup H is 1, minus 1. Obviously, we can see it's a subgroup because 1 and minus 1 are inside G. So this is H is a subgroup of G, and the operation is multiplication. Now, we know that this group is an abelian group. So therefore, H is a normal subgroup of G. And we know that if the group is abelian, then all the subgroups are normal subgroups. Okay, this we have seen in the previous video. So here H is a normal subgroup of G, right? Now we will make the quotient group. How will we make the quotient group? So basically, quotient group contains all the cosets. So we have to make the cosets, okay, of H in G. So for that, we take one element of G and multiply with all the elements of H, you get one coset. You take another element of G, multiply with H, you get another coset. You take next element, next coset, next element, and the next coset. So this is how you will get 4 cosets. The number of cosets is equal to the number of elements of G. Okay, so that's what we are going to do here. We take 1 with H, so it will be H dot 1, which is a right coset. We can also make left coset and we're going to get the same result. Okay, so we are taking, you can just make it and check. So you're definitely going to get the same results. You take H, that is the subgroup, and first you take the first element of G. So it's going to be H into 1, which gives 1 and minus 1. Obviously 1 into 1 is 1 and 1 into minus 1 is minus 1. Now this thing is equal to what? The subgroup, right? It's 1 and minus 1. So this thing is H. That is H into 1 gives H. Then H into next element minus 1. So it will give you minus 1 and 1, which is also, if you write 1 or minus 1, or you write minus 1 or 1, it's the same thing, right? So it's also equal to H. Then you take iota. So then it will be iota into 1 is iota. Iota into minus 1 is minus iota. So you are getting H into iota. That is, you write this thing, right? Then you take minus iota. So you take H into minus iota will give you minus iota and iota, which is again similar to this. So this is also equal to Hi. So now you see that you have the 4 cosets. These 2 cosets are same and these 2 cosets are same, right? Therefore, what are the total cosets inside G by H? 2. Because you cannot write H 2 times, right? So you write H 1 time and then Hi 1 time. Therefore, G by H, which is the quotient group, is equal to H and H iota. Okay, so this is one of the quotient groups. Okay, so since it's a group, therefore we can make the composition table, and that's what the question is also asking us to do. It's asking us to make the composition table as well. So for the composition table, that is the K-list table, how do you do that? You will have the operation here, and then the elements. The first element is H, and then second is Hi. So you have H and Hi here, H and Hi here. H into H is H, H into Hi is Hi, I into H is Hi, and then Hi into Hi is H. Okay, so this is the composition table for G by H. Alright, that's how you perform questions on quotient group. So if you have any quotient, if you have to find any quotient group, this is how you do. You make the cosets, and then you'll see what are the common cosets. You add them together like that. Okay, we'll take another example. Find quotient group G by H and also prepares composition table when G is equal to integers with addition and H is equal to 4 into Z with addition. So 4 into Z means only those integers that are multiples of 4. Okay, that's the subgroup. So since this is a commutative group, therefore 4Z is a normal subgroup of Z. For any commutative group, it's always, all the subgroups are going to be normal subgroups. Okay, if you have a commutative group, that is abelian group in other words. Okay, so for any abelian group or for any commutative group, the subgroups are always normal subgroups. So here also, since Z is a commutative group, it's an abelian group, therefore H is a normal subgroup. Okay, therefore G by H will exist. Okay, this is the first thing that you all have to check, if G by H exists or not. Okay, that's the first case. If it does not exist, obviously you cannot make the cosets, right? Now since it exists, so you can make the cosets. How will you make the cosets? Since addition, now you're going to do addition instead of multiplication as the previous example. So here, first you will take the first element from Z, 0, then second is 1, then 2, then 3, and so on. Okay, so what are you going to do? First you can do from the left or the right. It's going to be the same thing as I said in the previous example. Now what are you going to do in 4Z? What is 4Z? means multiples of 4. So it will be 0, 4, 8, 12 and so on, and on the negative side it will be -4, -8, -12 and so on, right? So first you take 0. 0 plus h will give you the same group as it is. 1 plus h will give you, you add to 0, you add 1. 4 will become 5, 8 will become 9, -4 will become -3, -8 will become -7. Okay, then you keep doing with 2, and then you do with 3. Now when you will do with 4, what will happen? When you do with 4, 0 plus 4 will become 4. 4 plus 4 will become 8. -4 plus 4 will become 0. Okay, so what do we see? We are seeing a repetition now. Okay, so I will just write it here in place of, so when you're doing h plus 4, okay, it means 0 will become 4, -4 will become 0, this will become 0, this will become 4, this will become 8, this will become 12, so on. Okay, and here in place of -8 you will have -4, in place of -12 you will have -8. Okay, and so on. So isn't this thing synonymous to this? It's the same thing, right? Because you're going to get the uh, same group. You are having 0, 4, 8. Here also you have 0, 4, 8 and so on. You have 0, -4, -8, 0, -4, -8 and so on. So basically h plus 4 is equal to h plus 0. Okay, so this is where you're getting a repetition. Okay, so this means that h plus 0 is h, right? So h is equal to h plus 4. If you do the same thing with 8, you are going to get the same h. So h plus 8 is also equal to h, h plus 12 is also equal to h, and similarly on the negative side, h plus -4 will be equal to h, h plus -8 will be equal to h, and so on. In the same way, when you do with h plus 5, so you will get h plus 1. Okay, you can do it and check, right? So this means h plus 1 is equal to h plus 5 plus h plus 9, which is equal to h plus 13 and so on. And similarly on the negative side, again h plus 2 will be equal to h plus 6, which will be equal to h plus 10 and so on, also on the negative side. And similar is the case with h plus 3. So in this way, everything is going to get repeated. Okay, what does this mean? That these are only the unique ones, okay, and the rest are all repetitions. Therefore the quotient group will have what? It will have these 4 cossets. Okay, thus h has 4 distinct cossets. So only distinct cossets are part of the quotient group, the unique ones. The rest, which are the repetitions, will not be added inside the quotient group. Okay, so therefore the unique ones or the distinct ones are h, h plus 1, h plus 2 and h plus 3. In the previous example you had h, h and h iota, right? The distinct ones were h and h iota. The other two were the repetitions. Okay, so similarly it's the same case here. Alright, so the 4 distinct cossets that are part of the quotient group are h, h plus 1, h plus 2 and h plus 3. Now you have to make the composition table. So again the same thing, h will give you h, h plus 1 gives h plus 1, so this gives h plus 2, h plus 3. Again here you have the same thing, so just keep writing and you will get the entire thing. This shows that what? H is the identity. Okay, because with h everything is repeated. Here also with h everything is repeated. H is the identity element. Okay, then the inverse of h plus 1 is what? H plus 3. The area where you are getting the table, the part of the table where you get the identity, right? You get identity here. Therefore the inverse of h plus 3 is h plus 1. The inverse of h plus 2 is h plus 2, which is self inverse, and the inverse of h plus 3 is h plus 1 again. Alright, so this is how you will make the Cayley's table for this quotient group. Alright, now let's move on to the 2 theorems related to quotient groups. First one, these are very easy theorems. Every quotient group of an abelian group is abelian, but not conversely. Okay, this is abelian. What is it saying? Every quotient group, let's say the quotient group is G over H. Okay, every quotient group of an abelian group, so the group is abelian, means it's commutative. Okay, that is AB is equal to BA. Alright, but not conversely. So let's see how do we prove that. So we will take the quotient group G by H, and since the group is abelian, so it means what? Let H be a normal subgroup of G. Since we are having a quotient group, therefore H has to be a normal subgroup, right? This is given to us, so we will say that H is a normal subgroup of an abelian group G, and A is element of G, B is element of G. Then since A belongs to G and B belongs to G, then what does it mean? That HA belongs to G by H and HB belongs to G by H. That is, the H is a normal subgroup, right? And for making the quotient group G by H, we need to have the cosets, right? And since A and B are element of G, so therefore HA is element of G by H and HB is element of G by H. Understood till here? Now, since the quotient group is given to us, right? Therefore, we can use the definition of the quotient group, which is HAHB is equal to HAB, right? Now, since G is commutative, that is, it's abelian. Therefore, AB can be written as BA. So HAB can be written as HBA. Now, when you open, so since when we had HAB, it was HAHB, right? So when we will have HBA, it will be what? HBHA, right? Therefore, HAHB is equal to HBHA. So what does it mean? That this is one element of the quotient group, another element of the quotient group. When multiplied in this direction or multiply in the opposite direction, it's the same thing. Therefore, both of them are equal. So we can say that the commutative property is true. That is, HA element of G by H, HP element of G by H, which implies HAHB is equal to HBHA. So G by H is also commutative. This is the property of commutativity that we are proving, right? Because we have to prove that every quotient group of an abelian group is abelian. We have to prove that the quotient group is abelian. To prove that the quotient group is abelian, what do we need to do? We have to prove this property. That is, AB is equal to BA. For a quotient group, it will be HAHB is equal to HBHA. Alright, so that's the simplest way in which we can do this theorem. Now for converse, okay, it's saying that but not conversely. So in conversely, it's not true, because for example, we take the example of an abelian group, which is S3 by A3. This is a quotient group, okay, where S3 is the symmetric group S3, A3 is the sorry, A3 is the subgroup of S3. It's the alternating group, right? So what does it mean? That A3 is having all those elements of A3 are inside S3, right? So this is a quotient group, right? A3 is a normal subgroup of S3. This thing is an abelian group, all right, while S3 itself is non-abelian, because we know that S1 and S2 are abelian, S3 is not abelian. Again, this we have done in the video of permutation and symmetric group, where I explained S3 in detail, and I also told you that you have to remember this particular property, because this is what we are going to use in the theorems, right? So remember, S1 and S2 are abelian, S3 is not abelian. Okay, so the group itself is not abelian, right? But the quotient group is abelian. Okay, this is what it's basically saying. Okay, so every quotient group of an abelian group is abelian, but not conversely. Means every group won't be abelian in that case. Okay. All right. Theorem number 2. Every quotient group of a cyclic group is cyclic, but not conversely. So now, before you had the abelian group, now you're talking about a cyclic group. Okay. So same thing we are going to do. We're taking normal subgroup H and G, since it's cyclic. Therefore, now the condition is G is equal to generated by A. In the previous one, we were talking about abelian, so we took the property AB is equal to BA. Here we are talking about a cyclic group, so we are going to take the property of cyclic group, which is that is it's generated by A, let's suppose. Okay. Now, since every element of G is of the form A raised to n, because it's a cyclic group, so all elements are to some power of A, right? Since it's generated by A, and n is element of Z. Therefore, H A raised to n belongs to G by H. So subgroup, the normal subgroup H that we have here, with that we have to take all the elements of G and make the cosets, right? That will be part of the quotient group. So those will be H A raised to n. So A raised to n could be A raised to 1, A raised to 2, and so on, all the elements of G. Okay, so the coset will be H with A raised to n, and that will belong to what? It will belong to G over H, since it's a coset, right? Now, H A raised to n can be written as what? H into A raised to n means A n times, right? This will be written as what? A n times, so it will be H when multiplied, it will become HA, so on n times, right? So this means what? That HA is n times. So HA the whole raised to n, right? According to this, you can write it in this form. This shows what? That since ha raised to n means that one element is ha and it can have any power. So this proves that g by h is generated by ha, and the generator is what? And the element is what? ha raised to n. Similarly, like this, where a raised to n was the element, in the similar manner, ha raised to n is the element here. And we know that ha raised to n is the element of g by h. So this shows that, this part shows that g by h is also cyclic because it's generated by ha n. Okay, this can be ha raised to 1, ha raised to 2, ha raised to 3, and so on. All the elements are in the power of n. Alright, therefore g by h is also cyclic with generator ha, with the generator ha. It can be ha1, ha2, ha3, and so on. Okay, so this is how you will do the theorem number 2. But the converse is not true. S3 by A3, again we know it's a quotient group, is order 2 necessarily cyclic, but S3 is not cyclic. Okay, so this also we have seen in the examples. So you have to remember the converse for both the theorems. The converse is the same, that S3 by A3 is a cyclic group, is a abelian group, but S3 is neither abelian nor cyclic. Okay. Alright, so that's it for this video. I hope you understood the concepts. If you have any queries, you can type them down in the comment box below. Make sure to let me know what all topics you might want me to try and explain to you. Also, if you have any question related to examples or any past paper questions that you want me to solve, I'm already always available. Make sure you type them down in the comment box below. Make sure to like, share, and subscribe to my channel because that's what I need the most at this moment. Thanks a lot and stay tuned for the next one. Bye bye.